Okay, so everything I just said is not recorded, but oh well. I think you can figure it out. Okay, so we're going to talk about proving algorithms correct. So typically, we kind of break this down into two parts. So break into two parts. So piece one is to prove the algorithm terminates. And what we mean by that is it stops in a finite amount of time for any input. Finite amount of time for any input. Right? It's not very useful if we have algorithms that sometimes just go off and never stop. Now, I mean, maybe you could clarify that you could make this a little more precise and say, well, there's certain inputs that we don't care about, and it's okay if it runs forever on those, but maybe some subset of inputs we care about that it runs. Fine, we can make that distinction if we need to, but typically we want our algorithms to stop in some finite amount of time. Okay, and then part two is we prove that if the algorithm terminates, it produces the correct output. Right, and what do we mean by correct? Right, we mean correct, with respect to some specification, like maybe a mathematical specification, or some, brute force algorithm, etc. Right, for any given algorithm, we're going to have some idea in mind of what it would mean for it to be correct, right? Like what the correct output is. You don't always have to do it in these two steps, but it often kind of works nicely to separate it into these two things. So that while you're proving that the output is correct, you don't really have to worry about, you're just assuming like, oh, it's always going to stop. And then when it stops, I need to think about what I'm going to get. And then separately, you can just prove, I don't care what output it gives, but I'm just going to prove that it's always going to eventually stop. And, and sometimes the fact that it always stops is just going to be obvious. Like if the algorithm says, for every vertex in the graph, blah, blah, blah. And you're like, well, my graphs are finite, and it loops over all the vertices, so it's going to go. This one, though, I mean, GCD, these algorithms, it's not quite so obvious. Maybe if you've tried them, you have a sense like, yeah, this is, things are getting smaller, or somehow it's like it's going to stop. But just looking at the code, it's not obvious that there's just like some loops that say while whatever, or it's some recursion, and you're like, what? Could be an infinite loop, could keep calling itself recursively forever. I don't know. We have to prove that. Okay. So any questions about that? So we're going to start with the easier one. So which do you think would be easier to prove something about, the iterative version or the recursive version? We vote. Let's vote. How many people think the one with recursion is going to be easier to prove stuff about? How many people think the one with a while loop is going to be easier to prove stuff about? Evenly split. That's good. Okay. The answer is recursion is way easier to prove things about because we can use induction. Induction and recursion are like peanut butter and peanut butter. Just loops are super annoying. Like they're really annoying to figure things about actually. No, but I mean we can do both. So we're gonna start with. So I'm gonna write out GCDR here, just to have it up here. So we have this GCDR AB says if B equals 0, then A, else GCDR B A mod B. Okay, and in this case, well, okay, no. First step is to prove that it always terminates. Okay, so we don't care about what output it gives. We just want to prove somehow that no matter what inputs we give it, it's eventually going to stop and return some kind of answer. So one, proof that GCDR terminates. Now, I guess we do actually have to be careful here about like what kind of inputs are we allowed to give it? Because actually we haven't really, it's kind of, I left it implicit, and really, to be precise, we have to say, what are the possible inputs here? Because like, you know, could A be like 2.4? Could it be like a string? I mean, so clearly not, right? But we need to say that. So let's say terminates for all, let's say natural number inputs. Oops. Now, you can certainly make sure this algorithm works also for negatives. That's not necessarily a problem. It just doesn't really add anything to our discussion, so we're just going to stick with the simpler natural numbers. Okay, well, let's think about this. Why does GCDR always stop? Does anyone, like when you were going through some examples with your group, is there a sense of why this can't keep going forever? No?
A mod B is always going to turn into a smaller number that has the same greatest common divisor, and there are a finite amount of numbers that are smaller than the input with the same greatest common divisor.
Okay, so you're saying that this A mod B is, but that's somehow getting smaller.
I mean, definitionally, it needs to be smaller than B.
Yeah, well, it's not the definition, but that was one of the properties of mod that was on the activity, right? That A mod B is always less than B. And so if you look here at like, you know, the input to this was AB, and then here we're calling it again, but we're calling the second argument, we're calling it with A mod B, which is smaller than B, right? So if every time we call it recursively, this second argument is getting smaller, right? And if they're natural numbers, right? Natural numbers can't keep getting smaller forever, right? And this is why it's important that it's a natural number. If it was like real numbers and it was like, oh, you divide it by 2 every time, well, you're never going to reach 0. Like you can keep dividing by 2 forever. If you're talking about natural numbers getting smaller, eventually it's going to have to hit 0, right? And then the base case is, right, we have a case for when B gets to be 0, we stop. So formally, we say by induction, and I guess technically, if you can say it's by strong induction. Remember that strong and weak induction are logically equivalent, so it's not like necessary to say by strong induction. You can just say by induction, but we are going to use strong induction, and it can be helpful for a human reader to kind of know what to expect, right? So by strong induction on B, here's a question for you, just as an aside. The first argument, is that also always getting smaller? No, why not?
B could be larger than A on the input, and so A doesn't change.
Right, that's right. Yeah, like if B is bigger than A, then when it calls itself recursively, it uses B here, and that could be, that first argument could actually get bigger. But we don't care. As long as one of them is getting smaller. Now, I mean, in practice, what actually happens is that very first time it calls itself, they'll swap, and then from then on, both of them will be getting smaller. We don't need to be that precise about it, though. As long as we can just say, look, the second argument is always getting smaller, so it can't keep going forever. Doesn't really matter what happens to the first argument. It could be getting bigger every time. It could be jumping around wildly. We don't care. The second one's getting smaller. So by induction on B, so our base case, when B equals 0, well, GCDR, by definition, GCDR of A0 equals A. So it just immediately stops and we're done. In the for the induction step, we're going to say suppose. So, well, okay, I guess I'll say this. You know, let B be an arbitrary natural number. And suppose, so what's the thing we're going to suppose for our induction hypothesis? Well, we say we have this B, and we're going to suppose that for anything smaller than B, GCDR is going to stop. So if you call GCDR on anything with a second argument smaller than B, then like we're kind of assuming already that that will eventually stop. So we'll say suppose that GCDR of, I'll call it A prime and B prime will terminate for any A prime, we don't care what A prime is, and any B prime smaller than B. Okay, so we're trying to figure out what happens. The second argument is B, and we're saying we're going to assume that anything smaller than that we already know that will terminate. Now we just need to show that it's also going to terminate, and we call it with B. Okay, so I could say that we must show GCDR AB will terminate. Well, GCDR of AB, because we already handled the B equals 0 case, right? We know that the algorithm is going to take the else part. So it's gonna call itself like this. B A mod B. Right, but here's we already mentioned this, right? This is the key step. We know that A mod B is less than B. But A mod B is less than B. So by the induction hypothesis, this call to GCDR will terminate. Hence, so will GCDR AB. Right, because GCDR AB just takes does one step and then makes a recursive call to this thing that we know is going to terminate. So it will itself also terminate. Questions about this? Questions do you have? So if it's not obvious already, we're going to be doing a lot of induction in this class. So if that's scary to you, then I suggest you go review your notes from discrete or whatever. Actually, on the algorithms website, I have links to a whole bunch of resources about induction, like some videos of lectures, that like discrete lectures, like a document with some examples, etc. So if you feel shaky on induction, I would recommend that you go and review that stuff. And actually, the next homework assignment, homework 1, you'll be doing a ton of induction. Like on purpose, I put a ton of induction in there, just partly because it's what we're doing, and partly also just to make sure that you get a bunch of hard stuff. Okay. So, yes, Noah.
So is the claim of this proof that this algorithm will terminate in most B steps?
I did not claim that, but that is true, and we could very easily tweak the proof to say, to show that that's true. I mean, I guess it's kind of just an obvious corollary of the way we prove this, because if B is always getting smaller, like, you know, at worst, it could just go down by 1 every time, and so then it would take at most B steps. It turns out that you can say something much stronger than that. It doesn't take B steps. It takes much fewer than B steps, and you'll do that on the homework. But yeah, but right now we don't really care how many steps it takes, just that it's some finite number. Does that make sense? Yeah, if it took as many as B steps, then this would be a really terrible algorithm. Because if you imagine running it on, like, 5 billion and 7, whatever trillion something, like, that could take a really long time. But we know that in practice, this algorithm is actually very fast. Even on huge numbers like that, it's going to finish very fast. So it's actually much better than that. Okay. So step 2, right, we're going to prove that it's actually correct. Now, what do we mean that it's correct? Well, in this case, what we mean is we have in mind the idea of GCD, like the mathematical definition of what GCD is. And I'm going to write that like with lowercase GCD, right? Lowercase GCD means, so like when I say GCD, like this is like the math version. And when I write something like capital GCDR, right, this is a particular algorithm which we hope computes the same thing as the math GCD, right? But that's what we mean, that it's correct. We have a mathematical specification of something, right? But the definition of GCD, the way we define it in a math class, right, is not a very good way to compute it, right? Or it doesn't give you. So like we saw this on the activity you did the other day, where you it was like, what are we, a brute force algorithm for computing GCD? Like, well, obviously, since it's defined as like the greatest thing that divides both, just try all the numbers and see, pick the biggest thing that divides both, right? But that turns out to be a horribly inefficient way to compute it. And so, so we have this better algorithm, but at face value, it's not at all clear that they are talking about the same thing, right? So that's our goal. Our goal is to connect these and show that they actually are the same thing. So we're going to prove GCDR is correct, i.e., we really want to say something like for all natural numbers A and B, GCDR of AB equals, little GCD AB. That's what we want to show. So And actually, in a way, this is kind of a recap of something that I think we did in discrete. I think in discrete we did like kind of give a little bit of an argument why that algorithm is correct. But again, so there's a lemma that I'm not actually going to prove, but I'll just state it. If b is not equal to 0, then little GCD AB equals little GCD of A mod B. Right, the idea is you're trying to find the GCD of A and B, and you subtract some number of copies of B from A. It doesn't change the common divisor. Right? Because you can kind of, A and B, you can chop both of them into little copies of B. B is their common divisor, and if you're removing B's from A, like each B is made up of a bunch of B's, and so you're just removing a bunch of B's and still, like, you can still chop them up evenly into B's. That's like the very hand-wavy version of why this lemma is true. I'm not going to prove this because the proof just is a bunch of math, and that's not the point of what we're doing today. Yeah.
So did you mean to do A mod B, B instead of B?
I did.
Can you explain why?
Well,
Is that because you're just shrinking just A?
sorry, say that again.
Like, is that because like you're just making A smaller and trying to?
Yeah, well, you could state it with them switched, because GCD is symmetric, and we're going to use that fact, right? That you can swap the arguments, and it doesn't matter. The reason I did it this way, both so we get to use the fact that it's symmetric, and also because I guess like thinking about it just from a mathematical point of view, it just feels more natural to me to think about it this way, where I'm like, I have A and B, and I'm just like taking away some copies of B from A. And I'm not also like doing this swapping thing.
Extra.
The swapping thing is important for making sure that it stops, right? And that's part of why we did the algorithm that way. So yeah. So like there are kind of some meta reasons why I chose it like that, but it's not ultimately like, it doesn't matter. Like you could state it the other way and it would still be true. Yeah. Yeah. Other questions? So proof. See lecture notes. So I'll take this opportunity to say that I have a very large PDF of all my lecture notes from this class. All the lecture notes from all the lectures I've ever given in this class, which includes a bunch of stuff that I don't cover anymore. Anyway, so like there's a link to it posted on the website. So you can always go look at that if you wish. And sometimes, for example, in this case, like if you go look in the lecture notes, there is actually a complete proof of this in there just for completeness. So if you want to know the details of that proof, if you want to look at it, you can go do that. You could also go look at like notes from discrete or some other math class where maybe you have something like that too. Okay. So theorem. What's going on? Oh, that's why. All right, you are gonna die. Here we go. You're gonna die too. There we go. That's better. All right. My computer just ran out of memory, so it was like swapping to disk frantically, trying to keep up. Okay, so theorem. This, right? So for all A, B, for natural numbers, GCDR, AB equals little GCD of AB. This proof is also going to be by induction on B. So it turns out in this particular case, like we didn't actually really have to do that first step to prove that it terminates, because this theorem kind of implies that already. Because if we're saying, look, for any inputs, it's going to be equal to the mathematical GCD, like, well, it has to stop in order to, like our proof is going to kind of show that it terminates as well. But I did it this way just to, because it's often a useful thing to separate out those arguments. So by induction on B, in the base case, well, GCDR of A0 equals, we just look at the implementation and we see what it does. If B equals 0, then it returns A, right, equals A, right? But now we have to say, well, what is the little GCD of A0? Now we have to think in terms of what is the definition of GCD. And this was one of the things you did on your activity, right? That A is in fact a common divisor of both A and 0. Right? A divides itself, anything divides 0, so the answer should be A. I just want to emphasize these are both equal to A, but for very different reasons, right? In one case, it's because that's just what the code says to do. In the other case, we had to think about what was the definition of what GCD means and argue why, you know, that should be the right answer. Right now, we're going to let pick some positive B, be a natural number. Right, I'm just saying B greater than 0 just because I've already handled the case when B is 0. Don't need to worry about that case anymore. So let's pick a different one. And suppose, you know, that for all B prime less than B, GCDR of A B prime equals little GCD of A B prime. I really should say, and for all A. Like, it doesn't matter what we put in there for A. It doesn't have to be some specific A. It's just like, as long as your second argument is less than B, then we know it's going to work. It's going to give us the right answer. Then, well, GCDR of AB equals, so since we know that B is greater than 0, by definition of how GCDR works, it's going to call itself recursively like this, B A mod B. So this is equal to GCDR of B A mod B. Right, so this is by definition of GCDR. Now, again, A mod B is less than B. So because of our induction hypothesis, we are assuming that this is equal to little GCD of B A mod B. Now we can swap these arguments around because GCD is symmetric. Right? How do we know that? just from the definition of GCD. The definition clearly doesn't make any distinction between the two. It's just like it's the biggest divisor that divides both. So the order of them doesn't matter, right? It'll be the same thing. But now we had that lemma that said, well, this is actually equal to GCD of AB. This is our lemma. And that's it. That's what we wanted to show, right? We wanted to show that this algorithm computed the GCD. Questions? I think that's my phone like buzzing in my backpack for some reason. Alrighty. On Wednesday, we will tackle proving that the iterative version is correct, which is going to be slightly more annoying, but in the end, kind of similar.